Okay, so this video is going to cover compound interest, but in this case, we're not going to be solving for an amount that's going to happen after a certain period of time. We're actually going to solve for some of these variables that would be in the exponent spot. Okay, so it's like an application problem for solving exponential equations. Okay. All right, so remember, if you're compounding over a set number of periods, okay, like daily or monthly or quarterly, semi-annually, annually, you would use this formula. If you're compounding continuously, remember we use the PERT formula here, okay? So let's look at example problem number 1. We've got a sum of $5,000 that was invested at an interest rate of 5% per year, okay? We want to find the time. Okay, so we want to find T, the number of years required to double your money. Okay, so first we're going to double the money if we're compounding semi-annually. All right, so we're going to use this formula. So make sure we use the correct formula. And then let's label, let's put values on all the variables that we know. Okay, so the amount that we're going to end up with is double what we invested. So that's where the $10,000 comes from. So the A is going to be 5,000 times 2, okay? P, the principal, the amount invested originally is $5,000. That's given here. R is the interest rate written as a decimal, so 5% we convert to 0.05. And N, remember the number of times that we are compounding per year is 2. Semi-annually means 2 compounding periods per year. And we're going to be solving for T, okay? So the first thing we need to recognize is that T is up here in an exponent location, all right? So we're going to have, once we plug all these values in, our variable is going to be in the exponent spot. So that means I've got an exponential equation that I have to solve, all right? So think back to solving exponential equations. We want to isolate the exponential piece of the equation, and then we're going to write the logarithm of each side. Okay, and that's going to be able to allow us to get the exponent here down on the main level so we can solve. All right, so first thing I want to do is divide by 5,000. Okay, now I can simplify what's in the parentheses here. So 0.05 divided by 2 is 0.025. Add that to 1. So over here on the right, I've got 1.025 to the 2t power. Okay. So now I've isolated the exponential piece of the equation. So now we can take the log of both sides, either the natural log or the common log. It's up to you. I'm going to use the common log. So the log of 2 equals the log of 1.025 to the 2t power. Okay? Now I'm going to use the power property to get the 2t down in front of this logarithm. Okay, so left side stays the same. Using the power property, the 2t becomes the coefficient. So 2t times log of 1.025. Okay? Now, we want to get t by itself, and to do that, I'm going to divide by 2 times log of 1.025. All right? So t equals log 2 divided by 2 times log 1.025. Now I can use a calculator to evaluate this. And it's going to double. My money's going to double from 5,000 to 10,000 in about 14.04 years. Okay? So that brings me to something called the rule of 72. Okay? It's not exact, all right? But if you divide 72 by whatever your interest rate is per year, okay, you should get the amount of time it's going to take to double your money. That rule of 72 only applies to doubling your money. Okay, so 72 divided by 5 is just a little over 14. So that kind of helps me feel like my answer here is pretty good. Okay, so in the same problem, same set of information here, what if we change our compounding from semi-annually to continuously? Okay, so if we're compounding continuously, my money should double a little bit quicker. Now it's not going to be significantly quicker, but it will be a little quicker. So it'll be less than 14 years. Okay. So make sure we use the correct formula. Continuous compounding means we use the PERT formula, okay? Let's label all the information we know. Again, we're doubling our money, so A is 10,000. Our initial investment was 5,000. My interest rate is 0.05, okay? So I got everything I need. Remember the number E here. E is not a variable, it's a number. So I don't need to put anything there, all right? So let's plug everything in, okay? We're gonna isolate this exponential piece here. So I'm gonna divide both sides by 5,000. So 2 equals e to the 0.05t, all right? Because e is my base, I'm gonna use the natural log this time. So let's take the natural log of both sides. And in the process, I'm gonna move my, my exponent down front using the power property, okay? So natural log of 2 equals 0.05t times natural log of e. Well, remember, natural log of e is 1, okay? So natural log of 2 equals 0.05t. Divide both sides by 0.05. Use a calculator, and we get approximately 13.86 years. So again, I knew it was going to be quicker than 14.04 years, but not significantly quicker. And you can see we've got a very small difference there. But still, that rule of 72 helps you understand that my answer is going to be somewhere around 14. Okay? All right, one more example. So we've got a sum of $1,000, and we're going to invest that at an interest rate of 4% per year. Okay? Find the time required for the amount to grow to $4,000 if interest is compounded continuously. Okay? So continuous compounding, we're going to use the PERT formula. Let's give values to everything we know. We want to have $4,000 at the end of this process, so A is 4,000, P is 1,000, and my interest rate is going to be 0.04. Okay, so let's plug everything in. All right, I'm going to divide both sides by 1,000. Okay, again, E is my base, so I'm going to use the natural log here. So natural log of 4. I'm going to use the power property to move my exponent down front. So equals 0.04t times natural log of e. Okay, remember, natural log of e is 1, so I can eliminate that. Okay, so natural log of 4 equals 0.04t. Divide both sides by 0.04, and then evaluate that on a calculator. So the time it takes to quadruple your money here from $1,000 to $4,000 is almost 35 years, so 34.66 years. Okay, and that's how you use the concept of solving exponential functions in a real world banking type of situation for compound interest.